Hello everyone, welcome back to another video. Till now we were seeing neural network as regressor or regressor means it will output a real number like 0.2, 0.3 or whatever it is. Now we will be seeing neural network as classifier means there will be different classes say dog, cat, crocodile, anything, and the neural network will choose one class. If the neural network chooses one class out of all the different classes, then it is called multi-class classifier. Okay. So today we will be seeing that multi-class classifier neural network. So first of all, what are the prerequisites that we need to know? First, we need to know about sigmoid function. So for binary classification, say you have only two classes. So like if you want to know if this thing is either dog or not a dog, then that is known as a binary classification. So for binary classification, as we have seen previously, there are multiple activation functions, say ReLU. So for binary classification, the specific activation function is called as sigmoid. Now, what is sigmoid activation function? As you can see, this formula here represents sigmoid activation function. So 1 by 1 plus e to the power minus x of whatever the input value is. So what it actually does is, if the value is close to 1, then it will make it 1, and if the value is close to 0, then it will make it 0. So that is the main function of sigmoid activation function. It forces the value to be either 0 or 1. So it will be helpful for us for classification. Say if it is a dog, then we output 1, and if it is not a dog, then we output 0. But if it was a regressor neural network, what will happen? It will output say 0.3. Now we won't know that 0.3 is yes dog or no not a dog. So sigmoid help us classify that real number output into either 0 or 1. That is for binary classification. So sigmoid is used for binary classification. Now what is softmax? Say you have a output, say you have a range of output here. Say you have yeah, say say you have 3, 4 and 3 again. So in this range of output where there are multiple outputs, not a single class, there are multiple class, and in that multiple class you need to choose one. If you see here, we can see that the 4 is the highest among all this. So we will select the zeroth class, first class, right? So we will say this is of type first class. Now, what this softmax does is this converts this like regression output or real number output into probabilities. Like this will convert it into say 0.3, comma 0.4, comma 0.3 into probabilities. So we can easily classify it. Like there is a 40% chance that the output will be of class 1, and there is a 30% chance that the output will be of class 0, and there is a 30% chance that the output is of second class. So what softmax does is similar to sigmoid but for multiple class. It converts the output into probabilities. It converts the output into probabilities that sums up to 1. Okay, this is what softmax does. Now, as you can understand by now, the softmax is used for multiple classes where there is multiple classes present, and sigmoid is used only when binary classification for binary classification. Now, we will be introducing another loss function. Previously, we have seen MSE or mean squared error as a loss function. Now, we will be seeing negative log likelihood. Now, I found a great paper or a great like blog that explains very well what is negative log likelihood, then what is log likelihood, and how is negative log likelihood different from cross entropy. So if you want to go more in depth, I will suggest you reading this paper. I will also give the link in description. But for now, what is negative log likelihood? Like for the higher level understanding, likelihood refers likelihood refers to the chances of some calculated parameter producing some known data. So you can also think of likelihood as probability. So the more the likelihood is same, like the our guessed probability that we are getting from software and the actual probability, the more they are same, the better for us. And negative means like the loss. Actually, likelihood represent what? The more the likelihood, the better we are predicting. But our neural networks are made for minimizing something. So we are minimizing the negative of the log likelihood. If you see this equation once, what is happening? Y1 is the actual value, yi is the actual value, and y hat is the predicted value. So this is the formula of negative log likelihood for binary classification. So what is happening? If y can be either like the predicted value or the actual value can be, sorry, the actual value can be either 0 or 1, and the predicted value can be any real number between 0 and 1. So what we are doing, we are taking the y1. If the actual value is 1, then this term we will get y1 into log of y hat. And if y1 is 1, then this term will get 0. So this whole term is 0 and negligible. But if ya is 0, then this term is negligible as ya is 0, and this term will show the negative log likelihood, like how much wrong we made the choice. Like if the real actual output is 0, but we predicted say 0.3, so our loss will be 1 into log of 1 minus 0.3. Okay, so this is negative log likelihood for binary classification. We are taking both the classes. It can be 0 or 1. Now this small one here is the function of negative log likelihood for multi-class classification. Now see what is happening here is we are taking the sum of all the classes present. So the classes present are like this is the value of y or y actual 0, 1, 0. There are three classes and one of them is right. And this is my predicted y or y dash, say 0.3, same 0.4, 0.3. So what is happening in this, if you see properly, we are only taking the value where y is 1, right? This this on top, this y in bracket, this is not actually power. This represents the, like, think, you can also think of this formula as like this: y multiplied with log of y dash, and that we are taking sum. Okay, so now when you take sum of all this, so what is happening when y is 0? So of course the term is becoming 0 and does not contribute in the sum. But when the y is 1, then only the sum, this function is contributing to the total sum. So what this actually does is it only takes the log likelihood of the correct or the true value and ignores the false values. And then we get our total loss, and according to that we calculate our gradient and move on. Now one more thing that we need to understand is what is the difference between our this negative log likelihood and cross entropy. So there is only one simple difference, that is cross entropy. Like cross entropy guarantees, like implicitly applies softness, but negative log likelihood does not have to implicitly apply softness. If we explicitly apply softmax on negative log likelihood, like before calculating negative log likelihood, then you can call it as cross entropy. So now let's move on to our code part. As you can see, let's go up. First of all, as always, we will import all the required classes. Then we will be importing our data. Now, if you see our data, there are multiple columns. Don't think much what these columns represent. You just think of them as parameters. So there are multiple parameters, and this is what we need to guess. Like so this is like a telescopic data, and after this we need to like calculate if from this telescopic data that it is a star, it is a galaxy, or it's a quasar. Okay, star, galaxy, quasar. It's like quasar is very little, so quasar examples are low. But we need to calculate it's either a star, it's a galaxy, or it's a quasar. Okay, so there are three classes. So this is a multi-class classification by neural network. So first, let us see what we are doing. So these are in strings. Of course, our neural network won't understand string. So first we need to convert this into numbers. So in this cell that only we are doing. If it's a galaxy, we are putting the number 0. If it's a star, we are putting the number 1. And if it's a quasar, we are putting the number 2. So let's run this cell. Okay. Now let's again see the data set one. If you see the class again, what is happening? See 1 1 0 1 1. So what it should be? Star star galaxy star 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 galaxy star star. Okay. So first we converted our classes from strings to numbers. Second, we are taking our predictor columns of the X column for our training data. And then we are taking our target columns or our Y column, that is classes. Then we are scaling the data using scikit-learn standard scaler. So what is scaling is, say this data is in the range of from 19 or say from 10 to 30. And this data is in the range of 180 to 300. So the range of the data is very different in different columns. This may affect the neural network because when we are calculating the gradient, maybe the gradient for this data is greater rather than the gradient for this data because it is 0 point something something. So what we need to do, we need to scale our data in order, like we need to scale and normalize our data in order to make the mean and variance proper. So that's only we are doing using standard scalar, and then we are splitting the data into train, validation and test. Okay. After scaling also, let us see what this data is looking like. So if we do train and we check the head, okay, one second, train is perfect. Okay, I think train is a NumPy array. Sorry. Huh. So see, the data is scaled between some range, say negative 1 to 1 or some common range. As you can see here, the data like this is in 0, 0.1, then 1 point something. So the data is scaled into some common range for better prediction. Okay. So next what we are doing, let me explain. So as we have in the previous video, we have understood how to make neural networks. So I am not going to build it from scratch. I have created this dense function. It is available in GitHub. You can check it under the helper folder. It is available. So what this dense function does is, it has the proper build of neural network, the forward and the backward pass, everything written under a class, and we are importing it, and on top of that we are building. So we will be focusing on the logic rather than again building it from scratch because we already once built that. So we are declaring our class classification neural network. First, we will be taking our learning rate LR, and then we will be creating a list of all the layers that we will be having in our neural net. Then for I in the range of length of the total number of layers we will be having minus 1, like all the hidden layers we are taking in this, we are creating a new layer self.layer.append using our that dense class that we have written separately. So using our dense class, we are creating a new layer. We are providing the input of that layer, the how many nodes are inputting into that layer, how many nodes are present into the layer as layer of size, and as we are not providing any activation function explicitly, so the activation will be ReLU. As you can see here, uh, wait, where is that? See, activation is true. Implicitly the activation is true, and we are providing value activation. So we are doing this for all the hidden classes. First we are appending that class, and then we are upgrading the input for the next class. Like why are we are upgrading the input? Because the output of the previous class becomes the input of the next class. I know you understand that. Now, next what we are doing, we are creating our last output, we are appending our last output layer, and we are not giving an activation in this. Why? Because from out we will be providing sigmoid. Next, we are defining our forward call. So forward call will be nothing but for every layer we are calling layer.forward, because in dense or in the helper function we already declared forward as a function. we are calling just looping and calling the function for every layer that we created. Similarly, in backward, we are looping and calling the function for every layer we created. Next, what we have to do, one more thing that we have to do, we need to encode our y variables. Let me explain why we need to encode our y variables. Is because see 0, 1, 2, these are all classes. But when we are providing this 0, 1 and 2, the network might take it as that 2 is greater than 0 or 2 is greater than 1 or 1 is less than 2. But that is not right. All of these three are classes and they are of equal importance. So what we need to do is, let me show you this here. So what we need to do is, we need to convert this and make it look like, say we have the class 1. So this one we will be converting to something like 0, 1, 0. This is called one hot encoding. So what is happening is we are expanding that. Now say we have 2. Okay, so this will become 0, 1, sorry, 0, 0, 1. So instead of using 1, 2, because that may confuse the neural net, we are using one hot encoding to provide one in the specific index of the class, so that every class has the same priority. Okay, so now let's go back, and as we see, so what is encoding doing? First, it is creating a zero array for the number of class. Here we have specifically three class: star, galaxy, and quasar. And for that 0, 1, 2, which index that class belongs to, it is converting that specific index to 1. Okay. So let's do a trial encoding and see. So for the test class y00, we are getting the array 0, 1, 0. So that means y00 must be what? Yes, y00 must be galaxy. So let's see that test y 0, 0, and we need to print it. Print it. See, so 0, 1. So in the zeroth, then in the first column, we are getting the like one hot encoding. Okay, so one hot encoding is working properly. We understood it. Now next is our softmax function. As I have already shown you, the softmax function here. This is the softmax function. So e to the power z of I by summation of e to the power zj for j equals to I to n or I to k. So you don't need to memorize this. You just need to understand what softmax actually does. What it actually does is converts the output into probabilities that sums up to 1. Okay. So this is the softmax function. We are taking the predictions as input, and we are converting, or we are normalizing it into our probabilities, and we are sending that back. Okay, now next is our multi-class loss or our cross entropy loss. So what is the cross entropy loss? As explained prior, cross entropy loss and like negative log likelihood, the only difference is cross entropy implicitly thinks that softmax is applied. So as we are using softmax, we can use cross entropy. You can check the blog I provided. If you read it once, you can get a more in-depth understanding what is cross entropy and how it is particularly different from negative log likelihood, but they are pretty much similar. So think of it as negative log likelihood itself. So what we are doing actual into log of predicted. Let us see the formula for this. So actual, wait, where is it? So this formula, sum of y into the log of predicted. That only we are doing actual into log of predicted. But this sum term POL we are adding. So what is POL? I have written here, we add a small tolerance to avoid taking the log of 0. So log of 0 is undefined, as we all know. That is going, if the log graph goes to the negative of infinity and we don't have a log of 0. So we are adding a small tolerance that if the predicted, but the predicted can be 0. For all we know, predicted can be 0. So if the predicted is 0, then our machine will fail in between. So we are adding a very small value, 1 into 10 to the power minus 6, so that the log does not give a error. Next, we are calculating our gradient. Our gradient is predicted minus actual. You may question that for MSC also gradient is predicted minus actual, and for this negative log likelihood also and the cross entropy also gradient is predicted minus actual. So if we differentiate directly, it won't come. But what we are forgetting is to pull the loss through the softmax function. So this is our softmax function. When we pull the loss through this and then we differentiate with respect to, like, we need to find, let's say this is zi, okay. So we actually, instead of dl by yi or our predicted value, what we need to find is dl by zi. Zi is our probability. So when we do that, when we find dl by zi, what we find out is that our gradient comes out to be predicted minus actual only. Next, let me run this one. Next, what we are doing, we are creating our loop. So let's see the loop line by line. First, we are declaring our learning rate 1 into 10 to the power minus 3. Then the number of epochs, that is 50 here. Then we are creating our model using our class that we have declared before here. This class, this here, classification neural net. So we are creating a model using our class classification neural net. We are passing on all the parameters. If you want to see what are the parameters here, the parameters are the output, number of outputs. This equals to 1. What is this? If you don't pass it, then the default will be 1. The number of input 13, the learning rate, and the layer sizes. So similarly, we are passing it here. So here the number of classes we have is 3. So the number of output we are passing 3. The number of input columns we have is 13. The input size is 13. Learning rate is our learning rate. And the layers we want is 25 node hidden layer and 3 node output layer. But now for every epoch, first we are declaring that loss of the epoch as 0. Then we are taking our xy from our train x and train y. This z function, what it does is, like, train x and train y one by one it will take properly. So for y, first we are encoding the values. Okay, encoding is like we are one hot encoding the values. Second, we are predicting the values and passing the prediction, like this model prediction, to our software, and that is our final prediction. Next, we are calculating our loss here, our multi-class loss, and then we are adding our loss to our total epoch loss. Then gradient we are calculating, and finally we are doing a back propagation and upgrading our gradients. And at every 10 epoch gap, what we were doing is we are taking the validation set, and for that validation set we are printing, you will see, first we are printing the epoch loss, then we are printing the, like, for x and target in validation set we are predicting the values, we are encoding our y, we are calculating our loss, and we are printing our validation loss. So let me run this one. As you can see, it's taking a little more time as the number of layer has increased from 10 to 25. So let it take time. As you can see, the loss is reducing steadily. Our validation loss is also reducing. That is a good sign, showing that our model is not overfitting to the data. So our final loss comes out to be 0.9 or 0.1, 0.09 or 0.1 almost. Our validation loss comes out to be 0.13. Next, one prediction we will do. Sorry, one prediction we will do. So for that prediction, we need this function. What this function does is, it takes the prediction and sees in which class it belongs to, and print out the string, because the user won't know that 0 is galaxy or 1 is star or 2 is quasar and whatever. So here we are doing our prediction. So for any particular n in the test set, we are calculating the prediction. We are model.forward, we are passing in our test for that particular, and this reshape is because the test of that particular may be not in array form, so we are converting it into array form in number of rows 1 and number of columns as needed. Then we are printing our prediction after the softmax, and then we are printing the predicted using this function here. So answer np dot argmax. What argmax does is argmax gives you the index of the maximum. Index of the argmax gives you the index of the, so argmax is giving you, as I told, index of the maximum. Now we are taking this index of the maximum, that particular index 0, 1 or 2 or whatever, and we are passing it to our function answer. Answer gives us the particular string, and we are also printing the actual string. Similarly, we are passing our test into the answer, and answer gives us the string. Okay, let's see this one. So as you can see, these are our predictions. If you add them up, they will come to 1. So 0.2, 0.79, like 79% it is saying it's a star, and 20% is saying it's a galaxy, and almost 0% is saying it's a quasar. Okay, let's see for some others. Let's for say 77. Okay, it predicted correctly. Then 65, correct again, and then 100, same correct. So as that's it for today. So what we learned is our activation functions such as softmax, sigmoid, and also a new method to calculate loss. Actually two, but both of more similar only. So negative loss likelihood. Okay. So thank you guys. If you like this video, please like, share, and subscribe. And in the next, please wait for the next video. Thank you.